I wanted to begin with reminding you of how did we get to where we are? Like, what is the problem that we're trying to figure out? And it starts like this. We know that water treatment plants, they have chemicals that they have to feed. And it turns out that feeding those chemicals is like absolutely critical. If you don't have a good chemical feed system, the plant won't work well. And my visits to many water treatment plants revealed that indeed it's commonly a problem in water treatment plants, that the chemical feed systems are prone to failure. I spoke with an engineer who was at the World Bank and was in charge of water projects on the continent of Africa. And he had this comment that water treatment plants that come in that are kind of these fully automated packaged plants, they have a life expectancy of about 3 years. And that means that the key option that we could have used, which is doing a fully automated system with computer control and pumps, we could have done that, and it would have had a life expectancy similar to your smartphone. So would have lasted about 3 years, and then there would have been serious problems with it. And so what we've been trying to do instead is to use smart fluids to come up with a completely different approach to doing chemical dosing so that there are as few moving parts as possible. And now, in these lectures that we're in right now, we're trying to figure out how to do that. And this is indeed the very first thing that the iWork Cloud program at Cornell attempted to figure out. So we looked at this one option, which is let's just have essentially a tank with a hole in the bottom. And we realized that we don't get constant flow rate. And that's because the pressure or the available energy that's there to push the chemical through the valve or orifice is decreasing as the chemical is being depleted because it's being used. And so that is like problem number one, that change in head of the stock tank is going to be causing us problems. That analysis, just as a little aside, does get us something interesting, and that is we'll use that to design the system for emptying tanks, for draining tanks, because that's what it's doing. It's draining a tank. And in a water treatment plant, we need to drain tanks. For example, this morning I was working on updating our flocculator, and the flocculator needs to have a drain system in it so that if you need to take it offline, you can open up some pipe ports and the system, the flocculator will drain quickly, and then you can do the maintenance on it. So there needs to be a design for that drain system. So that's coming up in a second. But I wanted to just stress that what we discovered so far that was difficult is that the amount of chemical in our stock tank is changing over time, or the flocculator tank is draining over time. And so the flow out is going to be changing as well. And we can figure that out by using a combination of the energy equation and perhaps a minor loss coefficient, a minor loss equation. So what we're looking for is a device that has a constant flow rate, even though the chemical stock tank levels are changing over time. So we need some way to have a constant source of energy, of head, that's pushing the chemical through our control system. We'd like it to be elegant and simple with few moving parts. And we're not happy with just one flow rate. We want the operator to be able to easily adjust something and get a whole range of flow rates, and to not have to do that by trial and error. So those are things that we would like. I said I'd do this quick aside of what's happening with draining a tank and trying to empty it. So you've got a tank, there's maybe an elbow at the bottom of that tank, and maybe there's a valve in that elbow. And the equation that I'm showing is actually kind of rework of the equation on the previous, like 2 slides back. And what it does is it relates to the minor loss coefficients, the sum of KE, all the minor loss coefficients, the height of the tank the width of the tank, the length of the tank, the time that you are willing to have it to take for this tank to drain, and it gets you a diameter of the pipe that's required. So it's a very simple, elegant equation that tells you how big the diameter should be on your bathtub drain if you want it to drain in less than 5 minutes, okay? So we use that equation or a similar version of it all the time. And just to, like, this is real, like the drains that are on the bottom of the said tank, that's part of what went into determining how big those valves needed to be. Oh, and you might say, well, how did you figure out what that drain time should be? And I don't know if you have any sense of this, but it's like there's a trade-off here, because if you want to drain the tank in 15 seconds, you're going to need a monster pipe and a monster valve, and that's going to cost you a lot of money. But if you say it takes a week, then your plant operator is highly annoyed at you because it took too long. So essentially, you're like trying to figure out, how long can I make this take and it not be annoying for the plant operator? And my guess is that that length of time for how long it take to take a unit process offline, drain it, it's something like 15 minutes. If it's taking longer than that, the plant operator is going to be like, why is this taking so long? So that's where that time came from. It actually, this is like trying to understand the world from a plant operator's perspective is what guides that decision. So now we know we've got this problem of the head or the level of the stock tank is varying. So we need to figure out a way to get that out of the problem. So we want constant head devices. And we're going to talk about a few. And I wanted to like tell you, like, where are we going? So this is just a preview of where we're going eventually, hopefully by the end of today. And this is a view of the entrance tank and our doser system that is going to control the dosing of chemicals into that tank is sitting here. Unfortunately, I don't have everything shown yet. So the tubes that connect to this are not yet drawn. Hopefully by the end of this course, that will all be finished and it'll be beautiful, but that's still a work in progress. So what happens if the flow rate through this entrance tank is 0, and you can see the scale on the wall there. If the flow is 0, the water level is way down in there, and there's a float on that lever system that is causing the lever system to angle and be, at this point, basically, to be horizontal. And then as the flow rate increases, so now I set the flow rate up to 50% of max. So this plant is designed for 20 liters per second. It's running now at 10 liters per second. The water level has come up in the entrance tank by 10 centimeters. And that lever system has pivoted, and the level of these two outlets, or outlets, has changed because of that. And that's, we'll connect to that eventually. So, and this is at an even higher flow rate through the plant. That lever system has moved even further. So this is our solution. And what we're going to do today is slowly walk through and figure out, how did we come up with this crazy design that ends up making it easy for a plant operator to adjust and control the chemical flow rate. So that was just like a teaser. Here's some of the pieces of that. So the first problem was, how do we get a constant head, which is get rid of the problem of the chemical level changing in the stock tanks. A really cool idea that's been around for a long time is that you have a tank with your chemical in it, and you have a float, think a little plastic basin that's sitting inside that tank. And there's a flexible tube, that's this vertical tube that I show here. Don't ask me how it's nice and vertical and also flexible, just don't ask. And the flow into this float is set by this little orifice that's letting chemical flow in. And the driving head is that delta H. That's what's pushing the chemical from the stock tank into that little float container. And then that little float container has an overflow, and it's falling in free fall down through that like a dosing tube. And that pipe has supercritical open channel flow, which means that it's free fall. And what's really important about this idea of free fall or supercritical flow is that anything that's happening downstream in that tube that is transporting our chemicals downstream, anything that's happening downstream cannot in any way influence how fast the chemical is entering at the top, because what's happening at the top is it's falling over the edge of a weir. And so downstream doesn't influence it at all. And if you're puzzled by that, if you are at Niagara Falls and you do something to increase the water level downstream of Niagara Falls, that has absolutely no influence on the amount of water going over Niagara Falls, right? So there's supercritical flow over Niagara Falls. What happens downstream is irrelevant to how much goes over. Climate change isn't going to affect us. Same thing happens here in that falling tube. And we're going to use that because that ends up being important. So unaffected by downstream conditions. Here's an example of this. Remember, I showed you this little tank sitting on top of a big tank, a little chlorine tank sitting on top of a distribution tank for a village. And what I didn't show you is the original design. So here's the original design. There was a little float, and that float might have been like 4 PVC pipes in a square held together with 4 different elbows. Did you all draw that in your head? 4 elbows holding together 4 pieces of PVC pipe to make a little frame. The air in the PVC pipes is, of course, low density, so that frame is going to float on the surface of the chemical. And that float is then connected to a flexible tube, and the flexible tube has an orifice in the side of it. So now it's almost the same as what we had before, maybe a little bit more elegant, where the pressure that's pushing the coagulant or the chlorine through that orifice is based on how deeply submerged that orifice is in the chemical. And as the chemical level drops, the float goes down with it. And so the height of chlorine above the orifice remains constant. So our goal is to adjust the flow rate and then somehow be able to maintain that flow at a constant, maintain it constant. That means that we have to control the head, and we can think of the head. I know this is, look, when they teach electrical engineers about electricity, they probably explained it that it's kind of like water. And so now as civil and environmental engineers, when we talk about water, we need to teach you that it's simple, it's kind of like electricity. So the head that is, wait a second, have you all, like at some point, like, I don't know, you learned something about resistance and voltage and current, like you got those relationships at some point? Maybe some of you have. Okay, so head, which is what we talk about in civil engineering, and we're referring to elevation change analogous to pressure. It's the energy available to push fluid through a flow resistance. That head is like a voltage drop, a change in voltage. And then we're going to have a flow resistance that could be the orifice. And on this flow resistance is like the resistor in an electrical circuit. So one option is an orifice. Another option is porous media. This is just like brainstorming about crazy things. We can put a bed of sand and have water flowing through sand, and the sand acts like a flow resistor. So this is true and a bad idea at the same time. Or we could have a long, straight, small diameter tube. Or we could have a short curved tube too, but the long, straight, small diameter tube is going to end up being the magic that we're going to use here. So those are three options for flow resistance. And then we're going to somehow vary the head or the flow resistance. So we could do either of those to vary the flow rate or the current. We could vary the head by adjusting the constant head tank elevation or the outlet elevation of a flexible tube, and I'll show how that's done in a little bit. Or we could vary the flow resistance by varying the orifice size. So we wanted to be able to vary the orifice size going into that tube. If there could have been a valve installed in the side of that tube and you could adjust that valve, adjusting a valve open and close is essentially opening and closing or changing the diameter of an orifice or changing the size of an orifice. So we could play with that. So I was looking at my notes this morning and realized, oh my goodness. So I had written on this slide who worked on this project. So this animation was created by students back in 2004. And one of these students, Peter Von Bucher, is working at Carollo and has been there for, I think, like 11 years or so. Another one, Rosalind Odom, has been connected with me for a very long time, working on the West Coast, and has also spent time in Honduras. So like there's all this love for these previous students who made these contributions to help move this forward. So this was their idea, 2004, of how you could create a constant flow device, constant and variable, meaning it stays constant when you want it to stay constant, but you can adjust it easily. So here it is. Hopefully, let's animate this guy. So there's water coming in through a float valve. The float valve closes off, and now that drip rate. Okay, I don't have mass conservation showed nicely, but okay. So now that float valve has closed off, so there's no more flow coming into this constant head tank. And now we have this small diameter tube that's connected to it, and that tube is going to be dripping. The float valve is our first trick. And I don't know if you guys know what a float valve is. And normally I would actually pass a float valve around to you in class and have you take it apart, but I didn't figure out how to do that in Zoom. You could go home and take the top of the tank off for your parents' toilet, and then you could close the valve off at the wall, and you could disconnect the float valve, and then you could look at it and see how it works, which I recommend that you not do without talking to your parents first. The float valve is what prevents your toilet tank from overflowing. There's a valve in the wall that is full on, ready to fill your toilet tank up. And there's this valve inside the toilet tank that when the water level comes up, it tips up, and as it's tipping up, it's closing itself off. So the float valve can be designed to maintain a relatively constant level in a tank. Just as a little aside, the float valve in the toilet tank doesn't maintain a constant level. If you just make a little leak in your toilet, and you can do this really easily, just open up the back of the toilet and lift the flapper a little bit and watch the water level drop, and the float valve won't turn on until the water level has dropped a little ways. That's a really cool feature of float valves in toilet tanks, so that when it does come on, you actually hear it, and that way you'll notice if the flapper is leaking, and you'll hear this cycling happening in your bathroom. That's designed to save you money. We actually want a float valve that is just simpler and will actually maintain almost a constant level in our constant level tank. And then we'll need to apply like an energy equation to this. So there's our friend, the energy equation. We're going to apply it between that control surface. Remember my little trick, and that horizontal surface coming off the end of the tube. And then everything goes away. Happily, the pressures are both atmospheric. The V going through those control surfaces is 0. There's no pump, there's no turbine. And so the head loss is just equal to the change in elevation between those two surfaces. So that's elegantly done. We know what our head loss is. And now we need to add an equation that connects head loss and flow. And this could be the Hagen-Poiseuille equation. I need to make sure I'm thinking about this right. So this is the Hagen-Poiseuille equation. And if we neglect minor losses, inlet and outlet and curved tubing losses, then we could just use that Hagen-Poiseuille equation. We'd be saying essentially that head loss, the total head loss is equal to the major losses, HF, and we can solve for Q. And guess what? This equation is beautiful. It shows that Q is proportional to HF. And if HF, the major losses, is equal to the total losses, that means that if I take the end of that tube and I move it up or down, I'll be able to adjust the flow rate. And it'll all happen in a nice linear way. And if I move the end of that tube up to the same level as the level of the chemical or the water in the constant level tank, Q will go to 0. Because if I move the end of that tube up to the dotted line in my drawing, then there's no driving head anymore. The driving head is now 0, and the flow will go to 0. So that's a really cool system. We are here neglecting minor losses, although you could, of course, bring them back in. So that is our first doser, and it's already pretty cool. It allows an operator to change the chemical flow rate, and it does it in a very simple way, just by moving a tube up and down.